there will be a discussion about the concepts only. Started the streaming, okay?
Okay.
Yeah. Is my screen visible?
Yes, ma'am.
Okay. So we'll begin with week 5. The week 5 concepts were the phylogeny construction problem. So in that we had discussed on what is an additive distance matrix. So additive distance matrix is if we have a simple tree. Simple tree is basically a tree which has either zero. A tree which doesn't have like more than two uh, sorry let me just give me 1 minute, okay? Yeah, hello. Okay, so simple tree is a tree without any degree to nodes. Like we cannot have a node with something like this. Okay, if we have a node with something like this, then we can just cut this node and merge the two edges with into one edge with node weights. Okay, so we don't have degree two nodes in a simple tree. So if for a additive, if given a distance matrix, if there is exactly unique simple tree, if there is a unique simple tree, that means there will be one simple tree and it will be unique, so then it is called as an additive distance matrix. Okay, so this is the definition of an additive distance matrix. If you are given an additive distance matrix, then the phylogeny tree that you can construct on this additive matrix, the simple tree that you can construct on this additive matrix will always be unique. Okay, we will be having exactly one simple tree. Okay, so now for the phylogeny construction problem, we had two different types of construction methods. One was the distance based phylogeny and there was the character based phylogeny. Okay, so from exam point of view, we will not be having this character based phylogeny method topics, only the distance based phylogeny topics will be there. Okay, so additive phylogeny algorithm, we were having these three different algorithms. One is additive phylogeny, neighbor joining, and ultrametric tree construction. Okay, so now this was the additive phylogeny algorithm. This is a formula to compute the limb length. This is a formula to compute how debolt. Okay, so you compute this limb length and debolt, and once you compute the limb length, then you compute debolt, and you remove these. You had chosen one of the you choose a node at random and you compute its limb length, then you subtract the limb length from the debolt, and you from the d matrix you get debolt, then you remove the row and column concerning that particular node. Okay, so you get d trimmed, then you keep on repeating that, and then finally we were adding the cherries and the nodes accordingly. The limb lengths will be according to this limb length, and we compute the cherries according to what nodes we have chosen. Okay, so yeah, this was the additive phylogeny algorithm. For the neighbor joining algorithm, we had the total distance. We compute the total distance, then we compute the D star matrix. Okay, the D star matrix we compute, and following this, we compute. Once we compute the D star matrix, we choose the one with the minimum. We choose the cherry. with the minimum value. There can be multiples, so we can choose. If there are multiples, we choose the one with anyone at random, but it should have the minimum value in the D star matrix. Okay, so we choose that one, and we merge them into one particular one cherry. So this I and J has been merged into M. Okay, so now this distance to these two values to the remaining cherries, okay, the remaining leaves, which was K and L. So distance of M, distance between K and L was known to us. This we knew from the original distance matrix, but we don't know the distance of this new cherry that we create, new leaf that we created using I and G. One we merged I and G into M. M is a new leaf. So from this new leaf, we don't know how to compute these distances. So we use this formula to compute the distances to these two leaves. Okay, so once we do that, we again repeat the same, and finally we have a matrix with just two leaves. So we add the distance between these two leaves as the node, and then add we expand each of them. M we had sorry, A we had compressed into K, and L we had compressed into A. So we expand K and L over here. Okay, and whatever was the distance from K to M was 10 here, so we subtract this to this is 4, so we subtract this from 10, so this 4 from 10 we are subtracting, and we get 6, so the limb length of K will be 6. Okay, and we repeat this. Okay, so this was the neighbor joining algorithm. Ultrametric evolutionary trees is the evolutionary tree where every node is having an age in some million years or billion years, depending upon the question. So whatever it is, so whatever is the age, we divide it accordingly. So the length of these edges represent the time. Okay, and the nodes at the below these nodes, they represent our uh, they represent the current species. Okay, so the internal nodes represent our ancestors. So this particular node with the age 2, it means that about 2 million years this ancestor had split and mutated into form two different species. One of them was chimpanzee and the other one is bonobo. Here it means that about 6 million years ago this ancestor has split into two, and one of the one form mutated into forming this particular ancestor, while the other ancestor mutated to form the human. Okay, so this is the meaning of the ultrametric evolutionary trees, and here is the algorithm example for the construction of the ultrametric tree. So we have IJKL, so these are our current species, and then we compute find the one with the minimum distance, which is between K and L. If there are multiples with the same distance and they are the minimum value, like suppose I and J was also having two, then we can choose either of them at random. Okay, so we can choose K and L, and as it is having the minimum distance. So now we choose K and L and we merge them into KL. Okay, so this is my new ancestor called KL. So now I don't know the distance of KL to other nodes. So we use this formula to compute the distance of KL to the other nodes. Okay, and then we repeat the same procedure and we construct the tree accordingly. Okay, so this was the ultrametric tree algorithm. Okay, now coming to the week 6, we have multiple pattern matching problem that we looked into the week 6. So we are given a reference genome text and a collection of sequences patterns. So we were having these patterns, and we had a long reference text, and we want to find the position where these patterns occurred as substrings in this text. Okay, let's say this is the DNA sequence. We want to know where this particular pattern, at what position this pattern occurred as a substring. So if we know the starting index, then it should be fine with us. Okay, so this was the multiple pattern matching problem. For that, we required suffix tries. We saw what suffix tries is. So we take the node and we expand every character into in one edge, and then we keep on doing that. So that's why we have the at the end in the leaves we add the suffix, the position from where this and where this suffix starts. Okay, if it is a substring, then it will somewhere in between. But if it is a suffix, then it will end at the leaf. Okay, and if you keep on matching the pattern as we had seen during the week 6 examples. Okay, then for suffix tries, from suffix tries, the problem was the extreme amount of large amount of space required to store the suffix tries. So we looked into suffix trees, which basically compressed all of these one in degree, one out degree nodes. A node with exactly in degree equals to one and out degree equals to one. So all of these nodes, we merged them. So this node BA and A S dollar, all of these from here till here, all of these nodes are having just one in degree and one out degree. So all of these nodes, we merged them into one and we formed this kind of a tree-like a structure. Okay, so if a node is having multiple out degrees, then we don't merge it, we don't trim it, we just trim the nodes with one out degree equals to one. Okay, so that way we constructed this suffix trace. So this actually had a smaller space complexity as compared to the suffix tries. Now, a very memory efficient way will be to store this suffix trace will be like this the suffix array. So to construct the suffix array, we find the list of all the suffixes, and then we arrange them, sort them. We sort all of these suffixes in alphabetical order. Each of these suffixes is a string itself, right? So we take all of the, we consider each of these suffixes as a string, and we construct uh, we sort these strings in alphabetical order. Okay, then whatever, let's say these are the suffixes, and for each of the suffixes, the first suffix in the alphabetical order occurs at what position, that goes to the that particular, that suffix of that the position for that particular suffix goes at that index in the suffix array. Okay, so that is how we construct the suffix array. So okay, that is how we construct the suffix array. So that way we constructed this suffix array for all of the for the string. Okay, so this suffix array actually encodes only the suffixes, not the entire string. So we look into Burrows-Wheeler transform. So for the Burrows-Wheeler transformation, we have this string. We cyclically rotate the string multiple times. Okay, and we get a one string, multiple strings. So each of these cyclic rotations can be considered as one string. So all of these strings we perform in alphabetical order. We sort them in alphabetical order. So once we sort them in alphabetical order, whatever is the last character in each of these strings, we take the last characters of each of these strings and combine them to form one string, which is the Burrows-Wheeler transformation of the original string. Now, because this is an encoding, we will require the inverse encoding also. So what it means is the not inverse encoding, the decoding procedure. This is an encoding, so we need a decoding also. What decoding means is obtaining the original string from the encoded string. So we have, this one is our encoded string, so we need the original string. Write down all of the characters. We know that this set of characters goes in the same sequence, that is the last column. Then in the first column is basically a sorted order of these characters. So we sort these characters and we get this sorted order in the first column. Then for repeated characters, we number them as 1, 2, 3, 4, 5, 6, and here, and we can number it as 1, 2, 3. So here the first occurrence of n, we number it as 1. Second occurrence of n, we number as 2. And third occurrence of n, we number as 3. Okay. For A1, A2, A3, A4, A5, A6, A is occurring 6 times. So we have numbered this 6 times. So here we see whatever is the first occurrence of A, that gets 1. Second occurrence of A gets 2. Third occurrence of A gets 3. And fourth occurrence of A gets 4. Fifth occurrence of A gets 5. And sixth occurrence of A gets 6. So now we start with dollar. So we have dollar here. So whatever is the last character in this row is S, so we put S before dollar. Okay, then we go to S, as A6 is here, so A6 comes before S. Now A6 before a6 we have n3 here, so n3 will come before a6, and we keep on repeating that, we will get the original string. There is a way to do it in the same like start in the other way also, like we start from this dollar. So whatever is the first character here, dollar, the first row was p, so p comes first. Okay, then we go to p, a3 is there. So one second. Okay. Yeah. So A3 is there. So we have A3 over here. And then we go to A3. The first character is N1. So N1 comes over here and so on. If you keep on repeating that, you will get the same original string again. Okay. So that is the inverse Burroughs Wheeler transformation method. The week 8 topics was on finding, this is for week 8, not week 7. Week 7 Livin will continue from where I'm like week 7 Livin will take over after this. So for week 8 we have this motive finding problem. We want to find compute motives. Yeah, one more important thing for week 6, there is something called as run length encoding. So here we have this Panama bananas, right? So let's say we have apple. Let's say we are having this string APPLEENA. Okay, so this is a string, and we want to encode it using another. There is another encoding method called as run length encoding. What it does is we takes the first character A and then sees what is the next character. If the next character is unique, it puts how many occurrences of A is occurring. So A is occurring exactly one time, so I have A1 over here. Then I take P. P is occurring two times consecutively, right? So I put P is 2. Then L is occurring exactly once consecutively, so we have L1. Okay. Then E is occurring three times consecutively, so I put E3. Okay. Then N is occurring once, so I have N1. A is occurring once, even though A had occurred previously, but here consecutively A is occurring exactly once, so I have A1 over here. So when I'm given this run length encoding, I can easily obtain this string by just expanding these characters exactly the same number of times, which is mentioned after that. So A1 is here. So I have A will be occurring exactly once. Then I have P2, which means there are two occurrences of P. So I put A, P and P. Then I have L1. So L is occurring once. Then I have E3. So E is occurring three times. So I put E three times. Then N is occurring once, so I put N one time. Then A is occurring once, so I put A one time. Okay. So this is what is called as the run length encoding. Okay. So now moving to week 8, we have the motif finding problem. So we have, we want, what is the motif? We have the short recurring pattern of DNA, which is called as a motif. So first we will look into we will look into how to score the motifs. To score the motifs, we have this set of motifs. We discussed how to compute the score of motifs, how to compute count of motifs, profile of motifs, consensus, and this motif logo. Okay, so there was this column wise motif entropy also. This logo was actually constructed using this column wise motif entropy. Whatever was the entropy for that column, for the particular character in that particular column, that this height represented that exactly the same thing. Okay, so this is how we had constructed the motif logo. Now this is the profile. Using the profile, so whenever if you are given this motif logo, then please check what exactly this y-axis represents. Okay, in this particular case, y-axis represents the column wise motif entropy value. It may be that I'll give like it may be the case that you are given count of motifs, a profile of motifs, or something like that. So you should check what this y-axis is, what the y-axis means. Okay, so some people actually use something else for this y-axis. This y-axis values vary in practical life. You can see that this y-axis varies to compute the motif logo. Okay, so you should check always what the y-axis means. Now there was the motif finding problem. We have the profile of the matrix, profile of the motifs. Using the profile, given the schema, using this profile, we can compute what is the probability of occurrence of this particular KEMA for this particular profile of the motifs. So using that, we can solve the motif finding problem. There were three different algorithms that we had discussed. One is the greedy motif search algorithm, then the randomized motif search algorithm, and the Gibbs sampling algorithm. Okay, so all these three algorithms, I am not going to discuss every one of them in details. You can look into how these algorithms are working, and you can let me know if you have any doubts regarding these algorithms. Now, Livin will um, take over for the week 7 content. I'll stop the uh, I'll stop the screen sharing, and we will continue for week 7. Following that, we'll discuss. Okay.
Ma'am, before the week 7 starts, can we request you to kindly share this PPT in the course material?
Yeah, we will share. Okay. Okay, we'll discuss this after the streaming. Okay. Levin, please continue.
Yeah, just a minute. So I'll quickly go through the concepts that are covered there. Week 7. So we have the K-means algorithm.
Sorry, your audio is not clear.
Is it better now?
It's slightly better, but I think it is not clear.
Is it is it okay now?
Yes, slightly better.
Okay. Yeah. So we have soft K-means, and then we go into the probabilistical modeling. There we see about mixture models, right? And like the Gaussian mixtures and so. Then, so initially we do this with the vanilla or simple formulation, extending K-means. Then we go to the probabilistical modeling where we say you have K-means with probabilistic, which essentially comes to one form of Gaussian mixture model. Right, soft K-means, so there are different variants in the soft K-means with the assumptions of the parameters, how we choose the variants to be, so ellipsoidal things, spherical things. So what are our assumptions? Based on that, the types vary. What is about the soft K-means thing, right? So in K-means, we have certain steps, right? Initially, the K-means algorithm goes like initialize weights, initialize the centers, and dumping them. And then we repeat convergence. What we do first, we compute the centers. Compute the clusters for each one, and update the centers with the new clusters. So in general, this algorithm is a very specific case of what we call as an EM algorithm. EM algorithm might not be introduced to now, but we'll think about it. Right? What is EM algorithm? Is expectation and maximization. Right? So the expectation step, we find the so in accordance with week 7, we find the responsibilities. Finding the responsibilities. So here, this cluster, the responsibilities is for each cluster center, for each point, what is the responsibility of a particular cluster is what we find. This is finding the responsibilities. Then maximization is the next step. That maximization is finding the parameters so that this clusters, the responsibility, we found the responsibility still. So we will be maximizing the log likelihood of that from speaking from the probabilistic model itself. It's basically maximizing the likelihood or the log likelihood, maximum likelihood, whatever likelihood. In terms of k-means, what we are doing is we are finding new cluster centers so that it maximizes the likelihood of the current assignment or the current responsibilities. That's what we system maximization step. Or maximize the our update centers so that maximizes the like the likelihood. Okay, so this is what we do in k-means. So the simple formula in which we extend soft k-means from k-means is that instead of using hard responsibilities, so here the responsibilities are hard, means it will be either 0 or 1, which means a cluster responsibility of a cluster to a particular data point is either 0 or 1, which means either that point belongs to the cluster or not. So in some sense, the soft k-means is called also sometimes called as fuzzy sequence, in the sense that we assume that this point, data point, need not only belong to one cluster. In some sense, it may belong to more than 2 clusters in a different membership values. Maybe it is very near to one, so it belongs to that cluster more, or it's slightly far away from another cluster, so it belongs to some level, maybe 80-20% kind of. So here, responsibilities are soft, which means it can lie between 0 to 1. So anyway, and then we do that, updating the cluster centers using the same formula that maximizes this. So how do we do this thing, updating the cluster? We find the mean, right? We find the mean to update the clusters usually. The mean of the data points that belonging to the cluster. Here, the mean is oops, yeah. Yeah. So here, like So here what we are updating, our updating is the mean. We are actually maximizing updating the mean of the clusters, that is the centers, so that it maximizes the likelihood of that. So here the parameter we are changing is updated is mean of clusters. Or if you assume it to be if we assume each cluster to be a distribution and the whole data set is a mixture of distributions, then this mean corresponds to the mean of each distribution mixture, right? Similarly, in case of k-means, we have to find the in the maximum likelihood. What we do is find the mean. But since here the responsibilities are soft, we kind of end up finding the expectation. Basically, this mean is the expected value of that. So when we do the math and arrive at the maximum likelihood estimation, we arrive at the expected value, which has the formula for the arithmetic. Similarly, when we do the probabilistic modeling, we arrive at the intuition. It will be a weighted mean. We use weighted mean to update because each data point will have certain belongingness to the particular center or a particular distribution. So we use weighted mean to update. So which is basically the kind of expected value of each cluster center. So we find the expected value for the membership to update the clusters. And the computational formula, how we do? Usually we compute the distance. We use distance to assign the clusters in the k-means. In soft k-means, we use a distance metric, but in a soft manner. So here we use the Euclidean distance and compare it to say that the lowest Euclidean distance is I will have the responsibility one, and the other clusters with less things will have. But here, since we have to assume a soft thing, how we use the distance? We use a kind of soft mean. So in general, there is a function called softmax. So here, what we do is kind of hard max. We only pick the cluster center with highest or the smaller, what do you say, smallest distance. So it's kind of very hard. So here we do something called as a softmax. So the softmax function is will be something like this. X of something, x of x, right? Contracts. Summation. Okay, but with this, I think it will be looking something similar to this. Here with this, we also add a kind of scaling factor or stiffness factor called beta. Okay, so this beta is basically, if the beta is more, we assume the variance of the distributions is less. That is to control the assumption. If we increase beta, we decrease the variance. If we decrease beta, we increase the variance. Sorry, if we decrease beta, we increase the variance. If we increase beta, we decrease the variance. So it's like to control our assumption on how spread the distributions are, right? So that's how that works. So this is in general, this e power x kind of thing is called a softmax function, and this gives us, like if you have some n numbers, it will give us probability distribution over n numbers with values lying between 0 and 1. If the value is high, so basically this is a sum over some numbers. So this is a monotonic function. It will give us a probability distribution. So kind of the numbers that we expect. Right? That is the vanilla formulation of that Sapir-Whorf algorithm. So here. And this is kind of empirical change from the hard responsibility thing. So this gives us the responsibility R of I, Ri, the responsibilities. Okay. With these responsibilities acts as the weights in this weighted mean calculation that we saw. Right? The weighted mean calculation is responsibilities acts as the weights for the cluster, the maximization scheme. So in the probabilistical modeling, probabilistical modeling. We assume instead of, like, this is a very general formulation, right? Assuming the mathematical softmax function, which kind of gives a probability distribution over that. So to like make this more interesting, what we do is we assume a probability distribution. So a mixture model. So what is a mixture model? So a mixture model usually consists of same kind of distribution, multiple same kind of distribution, and a mixture of those. So here we talk about Gaussian mixtures. So in that, what we have, so there will be multiple Gaussian distributions with different means and variance. So we do some certain assumptions on how the variance and the means look like. For example, we can each distribution will have a different mean. Right? If you see from this point of view, in k-means, we assume that each of this Gaussian distribution actually have same kind of variance. But we can change that assumption by using that variance assumption. So we can actually have clusters with different variance. So we have to add the parameters. So that. Okay. So in mixture models, the formula of how to compute the probability comes from, there are two things. One is the prior and the likely and the posterior. Okay. So we use kind of the Bayesian modeling to model this picture. So it will be like uh, there are n clusters or maybe k clusters. We can have k clusters. It means what is the prior refers to what is the probability of k, which means the probability of point belonging to a cluster. So that is the prior, right? Probability of a point belonging to a cluster. Then likelihood. If it belongs to the cluster, likelihood is like the if it belongs to the cluster, what is the probability or likelihood of a particular data point? Right. Posterior is like, in general, what is the probability of this particular data point in the mixture model? Or we can what is the probability distribution, the mixture distribution, the uh, mixture model in the whole. So that's how we do this. So it's like prior is like P of k or P of that particular cluster, probability of a point belonging to the particular cluster. Given any data point, what is the probability of that point belonging to the cluster? You can see probability of a particular cluster. C equal to small c. Yeah. This is like the probability of a particular data point given the cluster is, it's like x given c, and this is like in general, what is the probability? What is the probability of x in general? This is according to the model, right? Okay, this is not the posterior. This is actually the whole probability. And posterior is just the product of these prior and relative. Okay. So that's what we call the posterior, or the posterior probability. Yes, this is actually the posterior. These are- oh, this is in general the whole probability, right? The posterior is the posterior is this P of C given x, which means the probability of the particular data point belonging to a cluster. Okay. This is not the probability of this is actually this probability of the particular point belonging to the cluster. This is the probability of the cluster. probability that given probability that any data point from the data point belonging to the cluster. In general, what is the probability of that? What is probability of the cluster? It's kind of that. Generally, you take a bunch of data points. What's the probability of those that point be this in cluster? That is the probability of that cluster. Okay. So with this we do the probabilistical modeling, right? In that, this responsibilities will kind of become the probability of this particular the prior the cluster, right? That's how it works. In a Gaussian mixture model, we assume this prior and posterior probabilities. So what we assume is this this responsibility is kind of the posterior probability. What is the probability of this particular data point belonging to the cluster? Right. This is what we kind of this R1 becomes the posterior probability. To find that, we need the prior and the likely, all these things. What is the probability of the cluster? So assume you have 3 Gaussians. So with mean 0 and variance 1 and mean 1 and variance 2 and mean 2 and variance 3. So there are 3 Gaussians in here, right? So with this, the soft k-means formula kind of becomes, so this expression comes to this posterior. What we are trying to find is the posterior. And what is this? Is in general the marginal distribution over the right, which is basically the p of x. It gives you the p of x in some sense. And this is the likely. So this can be rewritten as the probability of this a point belonging to this particular or this any one of these cluster and multiplied by this given this cluster, what's the probability? So the normal distribution formula will have a certain e term, right? E to the power minus x by that. So usually this yeah, here actually we use this, we don't use the xi, we use the distance, right? Which is the given a data point, we use x minus c certain. So see, we can do some side like that, right? Some cluster or some cluster, it goes like that, and similarly here also. So yeah, kind of beautiful. So basically here also we compute the distance. So we softmax the distance in that case. So with the normal distribution formulations also we get equation something similar to this. Here we will have the variance constant with that, and also here you will have the distance. So in normal distribution you have the square term but divided by the variance standard deviation kind of thing. So that is also a form of square distance metric. So it can be also thought of a distance metric. And that's how the probabilistical modeling and the uh, vanilla modeling will go together, right? Because of this exponential distribution. So basically, the normal populations of the k-means are basically the generalization of the specific cases of the generic Gaussian mixture models. Right? Is that clear? So to look into the equations, let's look into the equations of them, the exact equations. Yeah. So here the Rk of particular data point. My screen is sorry. So here we model this using a Gaussian, right? So this pi k is what the probability or the prior, the probability of in general any given a point, the probability of it belonging to a particular cluster. Given any point, the probability of it. This is given that point belongs to that particular cluster. What is the probability of the likelihood of the data point? So that we use the normal distributions formula, which kind of comes very similar to the kind of thing that we have. Right? The exponential and the whole thing is whole thing sum that is coming in the denominator, right? And then we update the parameters. So here this is the weighted mean for us to update the parameters here in the here. So here we do the responsibilities with the weighted with the distance. So that's how we get the this arc is sum of just these R's. So that's basically the weighted mean formula. So with that, we update the standard deviations also. So that is this is the expectation and this is the maximization step. And we do this repeatedly. That's how it goes. We update the means also. This is for the variance, and we also update the means this way. Right. So this is a generic algorithm. For general GAM, we can do this. Right? So this case we are only updating in this case we are only updating the standard deviation. But in generic case, we can also apply that any models like this, right? Different variations. So this is the normal thing. We come with the responsibility. This is the E step. For the M step, we have to find the maximization. So for maximization, what we do is how do we arrive at these equations? So these equations is kind of we are maximizing the likelihood of the particular data point being the distribution. So with that derivation, we come up with these formulas, which is basically the weighted average for the mean. This is kind of a covariance matrix, people call it. So if you this covariance matrix can be different things. So it can be a diagonal thing, which means diagonal means each cluster will have a single variance, which means it's not a mixed variance. So you have only sigmas, and you can also have multi-dimensional variance. So if it has uniform variance across that, so that kind of things will be that affect the shape of the cluster that you come in. If you have a you can have a diagonal covariance matrix, or you can just have you can have a unit covariance matrix, or a spherical, or the full matrix. Everything we can have. So the equations of the normal distribution will change from the univariate normal distribution to the multivariate normal distribution. And how we arrive at these things, we will, I think, we will look into it at the week 8 or 9, where the expectation and maximization, the MLD, and how we do this. Right. So, any questions?
Do you guys have any questions for Levin?
Ma'am, to tell you honestly, week 7 is slightly tricky and it is quite mathematical. So we will have to revise and we will have to go to our machine learning foundation course, okay, where we were taught these concepts. So we'll have to revise, ma'am. Otherwise, it's okay.
Yeah. So to quickly recap, all these algorithms kind of share the same structure in which we do 2 steps. One is expectation and the maximization. In the expectation, we find the responsibilities. In hard K means it will be 0 or 1, or in the soft K means it will be something similar to a softmax function or mixture distribution as we see here. This mixture distribution will be something similar to a softmax function. If you expand it, it will be something like a exponential distribution. In the update step, what we kind of end up doing it, if you look into this equation, these equations are nothing other than a weighted mean. So here x is the value. So you can think it of like a expectation of x with this probability things. The responsibility somehow look like probabilities. So expectation is like this. So we kind of take look the weighted average. So this RK is basically sum of the small r's. So it is weighted average, and this is also a weighted average, but not with this x, but the squared error. You will see this is the squared error or variance kind of that. So it's the expectation of that, and this is basically the expectation of the weighted sum of this average of the responsibilities. The new K is somewhat like that. So that's the basic thing. This kind of structure follows all these algorithms. Right? So just the assumptions and parameters will change for each thing. For hard K means it is not a probability, it will be the 0 or 1. For soft, it will be a probability distribution. In the vanilla formulation, we use some form of softmax function, and in the other formulation, we use the probabilistic. And update step, we find the mean. In softmax, in the soft variance, you find the weighted mean. You can think it of in simple terms like that. Essentially, these are these things. Okay.
Okay, anything else? Okay, in that case, I'll stop the streaming. Okay. And
Okay,
then
ma'am. Yeah, yes, ma'am. Okay. So
Fine.
can we request the same thing, ma'am? Okay,
5
this,
minutes. 5 minutes.
yes, yes. Okay.
Yeah, okay. You were saying something?
Yes, ma'am. So